Hello, my name is Ashley Goodnight, and this is my Week 4 reading review for Physics 2212. In this week's EDX videos, the main topic we discussed was the electric fields of distributed charges. Let's go over the central idea before taking a look at some examples. There are 3 steps to follow in order to solve for the overall electric field of distributed charges. First, you must divide the charged object into smaller pieces, normally point charges. Then you compute the individual electric fields of all the pieces. And finally, you need to add them all up, yielding the net electric field. This last step can also be referred to as the superposition principle. Our first example is a uniformly charged rod. As you can see with the diagram on the left, we can think about a rod as particles stacked upon one another. Using the labeled line of symmetry, our E-field calculations become much simpler. The Y components cancel each other out, leaving the X components. We can mathematically solve for our field with an integral if we think about those point particles becoming infinitely small. This thinking results in the equation. We can further simplify this equation in 2 so-called limiting cases. We can modify the equation if 1, R is significantly larger than L, or 2, R is significantly smaller than L. The next example the EDX videos gave was calculating the E field of a charged ring. Similar to the uniformly charged rod, some of the axes will cancel when looking at the overall charge. In fact, both the X and Y components cancel, leaving only the Z direction. Again, we can mathematically solve for our field given the main equation. With an integral, this can be further simplified. This thinking results in the equation at the bottom. For our next example, we'll be looking at a charged plate. Now, instead of dividing the entire charged plate into point charges, we will think of the charged plate as a collection of concentric charged rings from our last example. This leads to the equation shown above. Like the charged rod, however, there are limiting cases that make our calculations much easier. If Z is significantly greater than R, we're far enough away from the plate that it looks like a point charge, and we'll calculate it as such. On the other hand, if Z is significantly smaller than R, the E field value will converge to a constant, assuming we are near the plate but not by an edge. The last example we took a look at this week was uniformly charged spheres. When talking about spheres, a sphere can be solid or hollow. We will make this distinction by calling hollow spheres shells, while referring to solid spheres as just spheres. When calculating their net E field, it is extremely important to know if our observation point is inside or outside of the sphere. If little r is greater than big R, we are outside. If little r is smaller than big R, we are inside of the sphere. Again, know that big R is the radius of the sphere, while little r is the distance from the center of the sphere to the observation point. I created this chart to easily represent how to solve for the net E field. Remember that when solving for a solid sphere from the inside of the sphere, we only care about the partial charge caused by the visualized concentric rings at the point of observation is outside of. This week's lessons apply directly to my major, electrical engineering. At Georgia Tech, EE majors select fields or threads to specialize in. 2 in specific, telecommunications and circuit technology, have required courses that build off what we're learning in this class. Those who follow telecommunications take ECE 4350, electromagnetic and microwave applications, while students studying circuit technology take ECE 4391, electromagnetic compatibility. That wraps up my introduction to Week 4. Thank you for listening.